Don't worry, it's simple. Just look at your watch. Now, I want you to ask yourself a question that probably hasn't crossed your mind since you were a child, staring at the ceiling, unable to sleep. What exactly are you watching? You're not looking at time. You're looking at a measurement, a number, a symbol. That's like pointing at a map and saying, "This is Paris." No, that's a representation of Paris. The ink and paper are not the city. In the same breath, the gears, the quartz crystal, the atomic vibrations in your phone's chip, they're not time. They're our desperate, brilliant attempt to pin down something that refuses to be pinned. We live inside it. We're carried by it from birth to death, like a leaf on a river's current. We structure our entire existence around its rhythm: morning coffee, afternoon meetings, anniversaries, deadlines, the last heartbeat. Yet, if I asked you to define it, right here, right now, you'd stumble. You'd use metaphors. A river, an arrow, a dimension. But you couldn't point to its substance, because time is the ghost in the machine of reality. And that ghost, I've come to believe, holds the key to the greatest journey humanity could ever undertake. This isn't just philosophy. This is the raw edge of physics. For most of human history, we got time spectacularly wrong. We thought it was universal, absolute, and steady, majestic, invisible clockwork, ticking at the same precise rate for everyone, everywhere. A king in his castle and a beggar in the street shared the same now. The past was fixed, the future was unwritten, and the present was this razor-thin slice of experience we all somehow agreed on. Then came a man with wild hair and a thought experiment that shattered that comfortable illusion forever. His name was Albert Einstein, and in 1905, with his theory of special relativity, he didn't just tweak our understanding of time. He set it on fire. Einstein's revelation was brutal in its simplicity. The faster you move through space, the slower you move through time. Let that sink in. It's not a metaphor. It's not science fiction. It's a law of the universe, as real and as enforceable as gravity. Time is not a single, universal soundtrack playing for all creation. It's a personal, local experience. Your rate of time depends entirely on your speed. If you and I are moving at different velocities, we are literally experiencing different flows of time. Our nows are not the same. I know how that sounds. It sounds impossible. It sounds like magic, but we have proven it definitively with the most accurate clocks ever built. Take two identical atomic clocks. These aren't grandfather clocks. They're miracles of engineering that measure time by the vibration of cesium atoms, so precise they wouldn't gain or lose a second in 100 million years. Synchronize them perfectly. Now, put one on a jet plane and fly it around the world at high speed. Leave the other one locked in a lab. When the traveling clock returns, you bring them together and compare. And the traveling clock is behind. It has experienced less time. It is literally younger than its stay-at-home twin by a tiny, almost laughable fraction nanoseconds. But the difference is there, measurable, unarguable. The clock that moved faster aged slower. This is called time dilation, and it is your first, trembling step onto the path of real-time travel. Think about what that means. If you could build a vehicle that moves at a significant fraction of the speed of light, say 90% of light speeds, and take a journey for what feels to you like 1 year, When you returned to Earth, more than 2 years would have passed for everyone you left behind. You would have leaped 1 year into Earth's future. You have traveled in time, not in imagination. In reality, but speed is only half the story. The other half is where things get truly strange, because Einstein had a second, even more revolutionary idea. 10 years after special relativity, he gave us general relativity. And here, he made the connection that changes everything. Time is woven into the very fabric of space. We used to think of the universe as a three-dimensional stage length, width, height, upon which events unfolded over time. Einstein said no. Space and time are not separate. They are fused into a single four-dimensional fabric. And this fabric is not rigid. It's soft. It's malleable. It can be stretched, compressed, and warped by what? By mass and energy. The more massive an object, the more it warps the space-time around it. Imagine space-time as a taut, stretched rubber sheet. Now place a heavy bowling ball star, a planet, in the center. The sheet dips, creating a curved, funnel-like depression. That's gravity. It's not a mysterious force reaching out and pulling things. It's the natural result of objects rolling along the curved grooves in space-time, down. Now, here's the critical mind-bending part. When space-time curves, it curves everything within it, including time. A clock placed closer to a massive object, like at sea level, on Earth will tick slower than a clock placed farther away, like on a mountaintop. Gravity doesn't just bend the paths of planets and light. It bends time itself. We've measured this too. In 1976, NASA's gravity probe launched a rocket carrying an atomic clock to an altitude of 10,000 kilometers. Compared to its identical twin on the ground, the clock in weaker gravity ticked faster. The difference was minuscule, but it was there. The universe was confirming its own strangeness, so we have two proven keys to manipulating time, velocity, and gravity. One lets you outrun the present. The other lets you sink into a slower stream of time. Both are passive forms of time travel. They can only take you one way forward. You can slow your personal time relative to the universe. Let the universe age around you, and then step out into its future. But you can't go back. Not with these methods alone. This is where most people stop. They think, okay, time travel to the future is theoretically possible, but going to the past, that's for movies. That's where physics draws the line. But does it? To understand if we can turn the ship around, we have to ask a much deeper, almost unsettling question. We experience time as a relentless, one-way flow, the arrow of time. Eggs smash and don't We remember yesterday, but not tomorrow. This feels so fundamental, it seems like a law. Yet, when you look at the fundamental equations of physics, from Newton to Einstein to quantum mechanics, they are almost entirely time-symmetric. They work just as well if you run the film backwards. The equations don't contain an arrow. They don't care about past or future. So where does our powerful, universal experience of time's direction come from? The answer lies not in the laws of motion, but in the laws of disorder. Entropy, the second law of thermodynamics, states that in a closed system, entropy, the degree of randomness or disorder, always increases. Things move from order to chaos. A hot cup of coffee disperses its heat into the cool room, never the other way. A sandcastle is washed away by the tide. Your childhood bedroom gets messier, not spontaneously tidier. This relentless increase in entropy gives us an arrow. It tells us which way the film is supposed to play. We define the past as a state of lower entropy and the future as a state of higher entropy. Our brains, our memories, our very consciousness may be processes that depend on this increase in disorder to function. We are creatures of the entropy gradient. This creates a fascinating and perhaps hopeful paradox. The fundamental laws don't forbid going backwards in time. They are ambivalent. The obstacle is not a law of thou shalt not, but a statistical one. It's not impossible for all the scattered molecules of smoke to rush back into a cigarette, for the splattered egg to leap off the floor and reassemble in your hand. It's just so astronomically, mind-crushingly improbable that it will never happen by chance in the lifetime of the universe. But what if we weren't relying on chance? What if we could use an engine? What if we could find a shortcut? Because Einstein's equations of warped space-time don't just allow for curved paths forward. Under certain extreme conditions, they allow for paths that loop. Imagine space-time not as a straight river flowing to the sea, but as a vast, turbulent ocean. In most places, the currents move in one direction forward, but in the maelstrom around a spinning black hole, or in the hypothetical structure of a wormhole, the equations suggest the currents could twist into a whirlpool, a closed loop, a path where, if you followed it, you would journey forward in time only to eventually circle back to the moment you started. Physicists call these closed time-like curves. A closed time-like curve is a theoretical path through the warped geometry of the universe, where the future leg of the journey connects back to the past leg. You leave Monday, travel, and arrive on Sunday, the day before you left. This is not fantasy. It is a valid, if exotic, solution to Einstein's field equations. The man who first found the most famous of these solutions was a mathematician named Kurt Gödel, friend of Einstein's in 1949. Einstein was deeply troubled by it. The math checked out. The universe's own rulebook seemed to permit time loops. The problem isn't the math. The problem is reality. To create such a violent twist in spacetime, you would need conditions of almost unimaginable extremity. You would need energies that make hydrogen bombs look like firecrackers. You would need to manipulate matter and forces at scales we can barely dream of. You would need, in short, to build a machine, not a DeLorean with a flux capacitor, but something far more profound, far more terrifying, and far more beautiful. But before we can talk about building, we have to face the universe's ultimate safeguards, the paradoxes. If going to the past is possible, what stops you from accidentally preventing your own birth? What stops reality from unraveling in a cascade of logical contradictions? I have stood at the whiteboard for hours, days, my hands stained with dry erase ink, wrestling with these questions. The grandfather paradox isn't just a plot device. It's a serious objection from the universe itself. It feels like a no-entry sign written into the logic of existence. Yet, when I look deeper into the quantum world, the realm of the impossibly small, I see glimmers of a different answer. In quantum mechanics, particles behave in ways that defy classical logic. They can be in two places at once. They can tunnel through barriers. And some interpretations suggest that every possible outcome of an event does happen. But in separate, branching universes, could this be the key? Could traveling to the past not change your past, but simply spin you off into a new, parallel branch of reality? A place where you can walk among dinosaurs or witness the pyramids being built without ever erasing the world you came from? Or is the universe smarter than that? Does it have a kind of cosmic censorship, a self-correcting mechanism that ensures any attempt to create a paradox simply fails, that every time loop is self-consistent? You were always meant to go back, and your actions there were always part of history. The keys are in our hands. Time dilation proves we can reach the future. The equations of general relativity whispered that the past might not be forever locked away. We stand at the border between the impossible and the merely unimaginably difficult. So I leave you with this question, the one that haunts my research and fuels my sleepless nights. If the universe's own laws provide the blueprint for a door to yesterday, what kind of key would we need to forge to turn the lock? And I want you to imagine the heaviest thing you can. Not a car, not a building. Think bigger. A mountain. The entire Earth, the sun 333,000 times more massive than our planet. Good. Now take that unimaginable weight, that sheer crushing IMMENSITY ... and compress it. Squeeze it down. Keep squeezing. Past the point where atoms collapse. Past the point where matter as we understand it ceases to exist. Keep squeezing until this object, this thing achieves what physicists call infinite density. You have just imagined the heart of a black hole, a singularity. Around this point of infinite warping lies a boundary from which nothing, not even light, can escape. The event horizon, a one-way membrane between the knowable universe and whatever lies beyond, a place where the laws of physics as we know them break down and scream in protest. Most depictions of black holes show them as cosmic vacuum cleaners, silent, dark, and passively hungry. But that's only half the story. Because to find our first potential time machine, we don't want a black hole that's just sitting there. We need one that's spinning. In 1963, a New Zealand mathematician named Roy Kerr solved Einstein's fiendishly complex field equations for a rotating black hole. His solution didn't just give us a new type of celestial object. It handed us a map to the most extreme environment in the universe and, with it, the first serious blueprint for a natural time machine. A Kerr black hole doesn't just possess mass. It possesses angular momentum. It spins at a significant fraction of the speed of light. And when something that massive spins, it doesn't just drag along the matter around. It drags space-time itself. Think of it like this. Place a bowling ball in a vat of thick honey. That's a non-spinning black hole warping space-time. Now, take that bowling ball and spin it rapidly. The honey around it doesn't just dip, it twists. It forms whirlpools and vortices. That's frame dragging, the literal twisting of the fabric of reality by a rotating mass around a Kerr black hole. This effect creates two remarkable regions. First, the familiar event horizon, the point of no return. But outside that lies a second, bizarre zone called the ergosphere, a flattened, rotating region of space-time that is being dragged around the black hole faster than the speed of light relative to distant stars. Let me be clear. Nothing can move through space faster than light. But space-time itself, that's a different matter. In the ergosphere, space is being pulled along so violently that to remain stationary, to not be swept around, you would have to move faster than light against the current. It's impossible. So, in the ergosphere, you are forced to move. You are a cork caught in a relativistic river, compelled to rotate with the black hole. This is where the magic, or rather, the terrifying physics happens within the ergosphere. The twisting of space-time is so severe that the normal, forward-directed flow of time begins to break down. The coordinates get mixed up. Pathways that normally lead only into the future begin to bend back on themselves. In the mathematical landscape of the Kerr solution, if you navigate the ergosphere with perfect precision, threading a path between being shredded by tidal forces and falling past the event horizon, you can, in theory, encounter a closed time-like curve, a path that loops back to where Ando Zoo started. Let's make this concrete with a thought experiment. Imagine we are a brave or foolish future civilization. We've built a ship of unimaginable strength, capable of withstanding tidal forces that would pull a person into spaghetti. We call it the Kronos Pilgrim. We pilot the Pilgrim to a safe orbit, just outside the ergosphere of a large Kerr black hole. Let's call it Chaos 9. Our mission: to enter the ergosphere. Perform a specific, pre-calculated maneuver. An exit from the perspective of mission control. Light years away, they watch our descent. As we cross into the ergosphere, our signals begin to distort. Our image on their screens slows down. Our voices drop to a deep drawl due to gravitational time dilation. Time is passing much more slowly for us near the immense gravity well. We fire our thrusters, not to escape, but to dive deeper into the twisting space-time. We are not fighting the current now. We are using it, surfing the relativistic vortex. According to our onboard computers, following the Kerr metric, we execute a Penrose-Manweaver-specific energy-extracting orbit first proposed by Roger Penrose for us on board. The flight lasts perhaps 10 minutes of bumpy, violent travel. We complete the loop, fire our engines at maximum to break free of the ergosphere's grip, and return to a safe distance. We hail mission control. Kronos Pilgrim maneuver complete. Returning to base. The voice that responds is unfamiliar. Kronos Pilgrim, this is Mission Control Delta. We ... We have no record of your scheduled return. Our logs show the Kronos Pilgrim was lost with all hands 127 years ago during the first ergosphere test flight. We have executed a closed time-like curve. Our flight through twisted space-time has thrown us over a century into Mission Control's future. We have used a black hole as a gravity slingshot through time, this is the critical, terrifying, but this is a one-way trip to the future. The Kerr black hole, as a natural time machine, seems to only offer forward journeys. To go backwards, we need more control. We need to not just ride the whirlpool, but plumb its depths. We need to venture closer to the singularity itself, and that's where the real nightmare begins. This realization leads us to a darker, more unsettling possibility. If manipulating space-time requires matter that defies normal physics, what if such matter already exists in nature, in concentrated, violent forms. What if the universe has already built the components of a time machine, and they are hiding in plain sight in the most destructive phenomena we know? Enter the wormhole, or as they were first named in 1935 by Einstein and his colleague Nathan Rosen, the Einstein-Rosen bridge. A wormhole is a hypothetical tunnel through space-time, connecting to distant points or to different times. Picture the universe as the surface of an apple. An ant walking from one side to the other must travel the long way around the curved surface. But if a worm bores through the apple's core, the ant can take the shortcut. A wormhole is that tunnel through the higher dimensional bulk of reality, creating a shortcut. The Einstein-Rosen bridge is not. It forms, pinches off, and destroys anything inside it faster than light or information can pass through. It's a mathematical connection, not a practical doorway. But what if we could prop it open? This brings us back, once again, to exotic matter. The throat of a wormhole wants to collapse under its own gravity instantaneously, to keep it open wide enough and long enough for something to pass through. You need to line the throat with a substance that exerts negative pressure. Exotic matter to act as a kind of anti-gravity scaffolding, pushing the walls of the tunnel apart. Imagine you could create a Finda, stable, traversable wormhole. You have two mouths, mouth A and mouth B, connected by the tunnel. According to the genius of theoretical physicists like Kip Thorne, who literally wrote the book on wormholes for Carl Sagan's Contact, this setup can become a time machine through a simple procedure. If you jump into mouth A, the older, earthbound mouth, you will emerge from mouth B, the younger mouth. But mouth B exists 9 years in the past, relative to mouth A's external time. You have traveled 9 years into the past. If you jump into mouth B, you will emerge from mouth A 9 years into the future. You have built a two-way time machine. The first step, the one-way jump to the future via time dilation, we already knew was possible. The second step, using the connected wormhole to turn that into a bridge to the past, is the revolutionary and terrifying part. But the universe, it seems, has a built-in safety catch. The wormhole time machine cannot be used to travel to a time before the machine was created. You can't go back to 1920 if your wormhole was created in 2050. The earliest you can visit is the moment mouth B returned from its journey, and the two mouths were first placed in proximity, creating the closed time loop. This is called the chronology protection conjecture in its weakest form, not an absolute ban, but a resetting of the clock to zero. However, this setup unleashes the specter of paradox in its purest form. With a two-way time machine, you can now, in theory, go back and meet your younger self. You can send messages to your own past. The universe's paradox police the laws of physics must. Do they prevent this entirely? Or do they allow it, but enforce a strange, consistent version of history where you were always part of events? We've now surveyed the landscape. We've seen how the raw, violent forces of nature spinning black holes can twist time into loops. We've seen how, in theory, we could mimic those effects on a smaller scale with impossible cylinders or warp bubbles. And we've seen how a connected bridge in space-time, a wormhole, could become the most elegant and potent time machine of all. Each concept is a mountaintop, and we are standing in the valley below, looking up. The paths are treacherous, littered with the wreckage of failed theories and insurmountable engineering hurdles. We need infinite cylinders. We need Jupiter's mass in exotic matter. We need to surf the ergosphere of a black hole without being vaporized. It feels hopeless. The obstacles aren't just big. They appear to be categorical vetoes from reality itself. But I want you to remember something. Remember the two atomic clocks. One on the jet, one on the ground. That tiny, almost imperceptible difference. That was the crack in the dam. That was the first proof that time is malleable. We are a species that looks at a crack and wonders what's on the other side. We are the species that saw a bird in flight and, within a single human lifespan, went from the first powered flight at Kitty Hawk to planting a flag on the moon. We took the mathematics of fission, which said a critical mass of uranium could release unimaginable energy. And for better or worse, we built a device that did just that. The blueprints are on the table. The equations permit it. The universe has shown us the cracks in time. The question is no longer if the laws of physics allow time travel. We've seen that they do. The real question, the daunting, thrilling, terrifying question that bridges the gap between the blackboard and the workshop is this. What kind of civilization would we need to become to move from understanding the geometry of time to engineering it? What materials would we have to invent? What energies would we have to harness? Would we need to become masters of stellar engineering, capable of dismantling planets for our raw materials? Would we need to tap into the quantum vacuum itself, harvesting the fleeting whispers of negative energy from the void? And most chillingly of all, if such a thing is possible, could it be that somewhere in the vast, dark stretches of cosmic time, someone or something has already done it? What if the key to time isn't found in the whirlpool of a black hole's event horizon, but in the silent, ghostly dance occurring inside every atom of your body, in every photon of light hitting your eye, in the very fabric of the vacuum we call empty space? Welcome to the quantum world. Here, the rules are not the grand, deterministic laws of Einstein. Here, the rules are written in probability, uncertainty, and paradox. Here, a particle can be in two places at once. It can be a wave and a particle simultaneously. It can disappear from one location and reappear in another without traveling the distance in between. It can know something about a particle on the other side of the universe instantaneously and, most unsettlingly for our journey in the quantum world, the very concept of cause and effect, the bedrock of our experience of time, begins to soften, to blur, and in some interpretations, to dissolve entirely. To understand how quantum physics might hold the key to time travel, we must first abandon everything we think we know about how reality works. We must step through the looking glass. Our story begins not with a machine, but with a cat, a thought experiment. In 1935, the Austrian physicist Erwin Schrödinger, deeply troubled by the implications of the new quantum theory, proposed a gruesome little puzzle to highlight its absurdity. Imagine a cat sealed in a steel box. In the box is a fiendish device, a single radioactive atom, a Geiger counter, a hammer, and a vial of poison. The atom has a 50% chance of decaying in the next hour. If it decays, the Geiger counter clicks, triggering the hammer to shatter the vial, releasing the poison and killing the cat. If it does not decay, the cat lives now. According to the Copenhagen interpretation of quantum mechanics, the mainstream view at the time a quantum system, like our radioactive atom, exists in a superposition of all its possible states until it is observed. It is both decayed and not decayed. Only when we open the box and look does the system collapse into one definite reality. But this means, for that hour, the cat itself must be in a superposition. It is both alive and dead, a grotesque, ghostly hybrid of existence and non-existence, waiting for an observer to seal its fate. Schrödinger meant this as a criticism. He was saying, this is nonsense. A cat cannot be both alive and dead. Therefore, your theory is incomplete. This is where we must turn to the most promising and controversial bridge between the quantum world and the possibility of tangible time travel. Quantum tunneling with temporal distortion. Quantum tunneling is a proven, everyday phenomenon in microelectronics. A particle, like an electron, hits a barrier it classically shouldn't have the energy to overcome. According to quantum mechanics, there's a probability that the particle will simply appear on the other side. It doesn't go over or through the barrier. It effectively takes a shortcut through the higher dimensional landscape of quantum possibility. How fast does this happen? In 1993, a series of experiments suggested something astonishing. Tunneling might be instantaneous, or, in some interpretations, it might even occur at speeds faster than light. More recent experiments are nuanced, but the consensus is that tunneling particles seem to bypass the normal space-time path altogether. If a particle can find a shortcut through space that effectively allows superluminal travel, then by the rules of relativity, it is also taking a shortcut through time. A tunneling particle could, from an outside perspective, arrive before it left now. Imagine not a single particle, but a coherent quantum state of many particles and object. Could an entire object tunnel through a space-time barrier? Could we create a region of space-time so warped, so repulsive, that it acts as a tunneling barrier in time, allowing an object to quantum mechanically jump from one moment to another? Theoretically, the Heisenberg uncertainty principle might allow it. The principle states delta E asterisk delta T is greater than or equal to K2. The uncertainty in energy delta E multiplied by the uncertainty in time t is greater than or equal to a very small constant, the reduced Planck constant, K. This means for a very short period of time, t, a quantum system can borrow a very large amount of energy delta E from the vacuum, as long as it pays it back quickly. This is how virtual particles pop into existence around black holes, leading to Hawking radiation. Could we, in principle, borrow enough energy to warp space-time on a macroscopic scale, just for an instant long enough for an object to tunnel through a temporal barrier? The energy required would be astronomical. The control required would be godlike. But the quantum rulebook, once again, does not explicitly say no. All of these quantum paths, many worlds, retrocausality, entanglement, tunneling converge on a single revolutionary idea. Perhaps we have been conceptualizing time travel incorrectly from the start. We imagine it as a journey, a ship moving along a timeline, a person stepping through a portal. But what if time travel at the quantum level is not a journey, but a reorganization? What if past, present, and future are like three cards in a deck? From our limited, classical perspective, we experience them in order: card 1, past; card 2, present; card 3, future. But from a quantum or a higher dimensional perspective, all three cards just are. They exist simultaneously. Time travel would then be the process of reordering your conscious experience of that deck, or, more radically, of physically reordering the deck itself. This is not science fiction. This is the essence of the block universe, or eternalist view, supported by general relativity, taken to its quantum conclusion. All moments exist in the four-dimensional block of spacetime. Our consciousness is a process that illuminates successive slices of the block, creating the illusion of flow. If this is true, then building a time machine isn't about creating a new path through time. The paths, all of them, already exist in the quantum multiverse. The machine would be a device that shifts your world line from one pre-existing path to another. It would be a quantum navigation system for the block universe. How could such a device work? We need a theory that doesn't just describe quantum weirdness, but unifies it with the gravitational spacetime of Einstein. We need a theory of quantum gravity. This is the holy grail of modern physics, and the leading candidate, string theory, offers glimpses of a reality where time travel might be not just possible, but perhaps even mundane from a higher dimensional perspective. String theory proposes that the fundamental constituents of reality are not point-like particles, but incredibly tiny, vibrating loops of string. The different vibrations of these strings give rise to all the particles and forces we see. Crucially, string theory requires more than the 4 dimensions we experience. It demands 10 or 11 dimensions of spacetime. The extra dimensions are complactified, curled up on scales a billion times smaller than an atom. But in these higher dimensions, the geometry of the universe could be fantastically complex. What we perceive as a particle's properties in 4D could be the shadow of a string vibrating in a convoluted, multi-dimensional shape in such a landscape. Our classical timeline might be like a river flowing across a vast, mountainous terrain. From the river's perspective, it flows one way, but from a bird's-eye view in the higher dimensions, one can see that the river sometimes loops back on itself, or that other rivers, other timelines, run parallel, separated by ridges of energy or topology. A time machine, in string theory, might be a device that can lift an object out of our 4-dimensional slice, move it through the compactified higher dimensions where the geometry of time is different, and then reinsert it into our slice at a different point along the temporal axis. It would be like an ant walking on a rolled-up newspaper. To get from point A to point B on the surface, it must walk a long way. But if the ant could briefly step off the 2D surface into the 3D room, it could hop to point B almost instantly. A string-theoretic time traveler would step off the 4D space-time manifold through the bulk of higher dimensional space and step back on at a different time. The engineering for this is, needless to say, beyond comprehension. It would require manipulating energies at the Planck scale 1019 GeV, a quadrillion times more powerful than the Large Hadron Collider. It would require stabilizing higher dimensional pathways. It is the stuff of cosmic, Type 3 Kardashev civilization dreams. But the conceptual point is vital. Quantum gravity theories, like string theory, do not erase the possibility of time travel. They often embed it in a richer, more complex geometric framework. This framework might also provide the ultimate answer to the paradox problem. The chronology protection conjecture, proposed by Stephen Hawking, suggested that the laws of physics might prevent time loops to avoid paradoxes. But in a quantum gravitational view, paradoxes might be resolved not by prevention, but by consistency. The work of physicists like Igor Nevikov formalized the Nevikov self-consistency principle. It states that if time travel to the past is possible, then events must play out in a way that is globally self-consistent. You cannot change the past because you are part of the past. Your attempts to create a paradox will always fail, forced by the very laws of physics to play out in a way that causes no contradiction in the quantum multiverse. This could mean your time-traveling actions were always part of the history of that particular universe branch. In the block universe view, it means your world line was always a closed, knotted, but consistent curve. You were always the mysterious stranger who gave your grandfather the idea to join the Navy. You were always the figure in the old photograph. The universe is a seamless, paradoxical tapestry, and time travel is just one of its threads. We have now descended from the cosmic scale of black holes to the subatomic realm of strings and probabilities. At both extremes, the message from the deepest laws we know is the same. Time is not the rigid, linear flow we perceive. It is a dimension, like space, that can, in principle, be navigated. The barriers are not legal, but practical. They are matters of energy scale, of material science, of control over forces that currently control us. The quantum view offers something the gravitational view lacked: a potential escape from paradoxes via the multiverse. It offers mechanisms retrocausality, entanglement, tunneling that treat time as fluid. It offers a theoretical framework, quantum gravity, that could, in principle, unify these mechanisms into a coherent technology. But it also presents a profound and unsettling philosophical challenge. If time travel via quantum multiverse hopping is possible, then which you is the real you? The one who stays in the original timeline, the one who branches off? If you travel to a past that is actually a new branch, are you really visiting your past, or just a nearly identical facsimile? The emotional core of time travel to correct a mistake, to see a lost loved one, might be a cruel illusion. You wouldn't be fixing your world. You'd be abandoning it for another dot. And if the block universe is true, and all moments exist eternally, then what does travel even mean? You are already at every point on your world line. A time machine would just be a device to change which slice of yourself you are consciously aware of. It would be less a vehicle and more a meditation technique, made physically manifest. Let's bring this back from philosophy to something resembling physics. Let's try to sketch, in the vaguest terms, what a quantum temporal displacement device might look like, based on our current, fragmented understanding. At the center of a Kerr black hole lies not a point singularity, but a ring singularity, a loop of infinite density. The mathematics suggest something astonishing. Because of the spinning, frame dragging, the region inside the event horizon might not be a pit of ultimate destruction. The Kerr solution describes an inner horizon and a theoretical region inside it, where gravity becomes repulsive, and pathways might exist that could lead out, not out into our universe, necessarily, but perhaps into another universe, another time, or through a tunnel in space-time. Some interpretations of the math suggest that passing through the ring singularity could be a portal, but could anything survive? The tidal forces near any singularity are beyond apocalyptic. They're called spaghetti. The gravity at your feet, pulled toward the singularity, is immeasurably stronger than the gravity at your head. You would be stretched into a strand of atoms. Furthermore, the inner horizon of a rotating black hole might not be a placid boundary. It could be a zone of infinite blue-shifted radiation, the entire future history of the universe, focused into a deadly wall of energy called a mass inflation singularity. Hitting it would be like hitting the Big Bang head dash on dot. So, the natural time machine exists in the equations, but it sits guarded by forces that make it seem utterly, practically inaccessible. A castle with a treasure at its center, surrounded by a moat of fire, walls of knives, and a dragon that is, itself, a rip in the fabric of cause and effect. This leaves us with a profound question. If nature can twist space-time into a time loop with sheer mass and spin, could we, with enough ingenuity, create a controlled, small-scale version of this effect? Could we build our own gentle, safe, Kerr black hole? This brings us to one of the most intriguing and controversial theoretical devices in all of physics, the Tipler cylinder. In 1974, astrophysicist Frank Tipler published a paper that sent shockwaves through the community. He took an earlier idea from Willem Jacob van Stockham and ran with it. He asked, what if you didn't need an entire black hole? What if you could create closed time-like curves with a sufficiently massive, sufficiently fast cylinder? Tipler's thought experiment was simple in concept, absurd in its engineering requirements. Imagine a cylinder made of an impossibly dense material, perhaps the density of a neutron star, where a sugar cube-sized piece would weigh as much as a mountain. Now, spin this cylinder, not at a few thousand RPMs. Spin it at a significant fraction of the speed of light, according to Tipler's solution of Einstein's equations. The space-time around this spinning supercylinder would become so twisted that it would create CTCs in its vicinity. You could orbit this cylinder in a specific path and return to your starting point before you left. There are, of course, catastrophic catches. First catch, the cylinder must be infinitely long. The Tipler solution only produces clean, paradox-free time loops with a cylinder of infinite length. A finite cylinder creates mathematical singularities at its ends, rips in space-time that would likely destroy the effect and anything nearby. We can't build something infinitely long. Some theorists have suggested that arranging multiple finite cylinders in a ring might approximate the effect, but the math gets fuzzy and the stability is questionable. Second catch, the material strength. The centrifugal forces on a cylinder spinning at relativistic speeds are, well, they're infinite. No known or theorized material could hold together. The bonds between atoms would be shattered by the mere thought of such rotation. You would need a material held together by something other than atomic forces, perhaps by the sheer tension of space-time itself, or by exotic matter with negative energy density, a concept we'll dive into deeply in the next chapter. Third catch, the energy. The rotational energy of such an object would be on the scale of a supernova. Containing and controlling that energy is a problem that makes fusion reactors look like child's play. So, the Tipler cylinder is, for now, a mathematical curiosity, a signpost that says time loops are conceptually possible with mass and rotation, but also a warning that says the practical requirements are indistinguishable from magic. But what if we're thinking too big? What if we don't need to warp all of space-time around us? What if we could create a tiny, localized bubble of warped space-time, a personal pocket of distorted time and carry it with us? This is the promise and the profound problem of the Alcubierre warp drive. The warp drive is not a time machine per se. It's a faster-than-light travel proposal. But as we know from special relativity, if you can outrun light, you are playing games with time. Alcubierre's brilliant insight was this: according to general relativity, nothing can move through local space faster than light. But there's no known limit on how fast space itself can expand or contract. So, don't move the ship through space. Move the space around the ship. Imagine a surfer on a wave. The surfer isn't propelling himself through the water. He's being carried by the wave's motion. The Alcubierre drive would create a warp bubble around a spacecraft. In front of the ship, space-time would be massively contracted. Behind the ship, space-time would be massively expanded. The bubble and the ship within it would be propelled forward like a surfboard on this wave of distorted geometry. Since the ship is at rest within the bubble, it feels no acceleration, no g-force. And since it's not moving through local space, it could, in theory, achieve effective speeds many times faster than light. Now, connect this to time travel. If you can travel faster than light, you can, under certain conditions, travel back in time. This is a staple of relativity. From the perspective of an outside observer, a ship traveling FTL could arrive at a destination before it left, according to some reference frames. But how do you create this warp bubble? Here we encounter the same monstrous problem that haunts every serious time travel concept. Exotic matter. To contract spacetime in front of the ship and expand it behind, you need a form of matter with negative energy density. Ordinary mass planets, people, stars, has positive energy density and creates attractive gravity, curving spacetime inward like the dip in the rubber sheet. To create the hill of expanded spacetime behind the ship, you need something with repulsive gravity, something that pushes spacetime outward. This is exotic matter. It's not antimatter, which has positive energy density. It's something far stranger. Theoretically, it would have negative mass and negative pressure. If you pushed it, it would move toward you. It's the kind of stuff that, if it exists, doesn't like to play by any of the rules we're familiar with. Does such a thing exist? Maybe, in tiny, quantum-sized amounts. The Casimir effect provides a tantalizing hint. Take two perfectly smooth, neutral, conductive metal plates and place them parallel to each other, incredibly close together in a vacuum. Classical physics says nothing should happen. But quantum physics tells us that the vacuum is not empty. It's a seething foam of virtual particles popping in and out of existence. These virtual particles create a tiny pressure. Between the plates, only virtual particles of certain wavelengths can exist. Outside the plates, all wavelengths can exist. This creates a slight imbalance, greater pressure on the outside of the plates than on the inside. The result? The plates are pushed together by the pressure of nothing. To a physicist, this force can be mathematically described as being caused by a region of negative energy density between the plates. It's a minuscule, microscopic effect, but it suggests that the laws of quantum field theory do permit negative energy densities. At least locally and temporarily, the Alcubierre drive, as originally calculated, would require an amount of negative energy equivalent to converting the mass of Jupiter into pure energy. It would also require the negative energy to be arranged in a shell thinner than an atom. Later refinements by physicists like Harold Sonny White at NASA's Eagleworks lab suggested that by oscillating the warp bubble's shape, the energy requirements could be reduced dramatically to the mass of a small spacecraft. But the problems are still staggering. How do you collect and stabilize macroscopic amounts of this quantum ephemera? How do you prevent the warp bubble from accumulating deadly Hawking radiation from virtual particles at its boundaries? How do you steer it? How do you stop it without unleashing the accumulated energy of 100 suns? The Alcubierre drive, like the Tipler cylinder, remains on the far side of a chasm of engineering impossibility. But it serves as another critical signpost. It tells us that the manipulation of space-time geometry for travel and, by extension, for time travel is not forbidden by the bedrock laws of physics. The obstacles are merely technological and material. They are questions of how, not of if, the laws allow it. Component 1. The decoherence shield. The first problem is quantum decoherence. Macroscopic objects are constantly interacting with their environment, air molecules, photons, etc., which collapses their quantum states and pins them to a single, classical reality. This is why you don't see cats in superpositions. To perform any large-scale quantum manipulation, like tunneling an object through time, you must isolate it from all environmental interaction. You need a perfect vacuum at absolute zero temperature, shielded from all electromagnetic and gravitational noise. A quantum cocoon. Component 2. The entanglement web. You would need to entangle the quantum state of the object you wish to send with a quantum anchor at the destination time. But since you can't send an anchor to the past, that's the problem we're trying to solve. You'd need a pre-existing, timeless entanglement link. This is where the block universe view could be key. You'd need to identify or create a quantum correlation that exists across time, not just space. Some theorists suggest that the quantum vacuum fluctuations themselves might contain such timeless correlations, faint, universal quantum foam that connects all points in SPIE's CETIME. Component 3. The retrocausal trigger, using a delayed choice-like mechanism. You would perform a quantum measurement after the intended displacement should have occurred, but which retrocausally determines that it did occur. You wouldn't send the object. You would, through a carefully orchestrated sequence of entangled measurements, force the universe to reconcile a history in which the object was at time B, not time A. You are not pushing the object down a time tunnel. You are rewriting the quantum history of a region of spacetime to include the object's displacement. Component 4. The consistency enforcer. A vast, planet-sized quantum computer running models based on the Nevikov principle. Before any displacement is triggered, it calculates every possible outcome, searching for the one that leads to zero paradoxes, zero conflicts with known data. It finds the self-consistent path, One where your appearance in 1920 doesn't change any newspaper headlines we've already read and then primes the retrocausal trigger to enforce that single consistent history. This sketch is, of course, a fantasy built on the edge of known physics. It is riddled with ifs and maybes. The energy required to manipulate quantum states on a macroscopic scale is unknown. The technology to create a timeless entanglement web is pure speculation. The idea of a retrocausal trigger is hotly debated, but compare this quantum sketch to the gravitational sketches from Chapter 2. The gravitational machines, the wormhole, the warp drive require us to command energies and materials on a stellar scale. We would need to be galactic engineers. The quantum machine, by contrast, requires control on an informational and probability scale. It requires not brute force, but supreme finesse. Not the strength to bend space-time, but the wisdom to rewrite history without leaving a trace. Which path is more impossible? The path of the giant or the path of the ghost? I don't know, but I know this. Every few years, a new quantum experiment reveals a fresh layer of reality's strangeness. We teleport quantum states across cities. We build quantum computers that solve problems in minutes that would take classical computers millennia. We create larger and larger objects that exhibit quantum behavior. Our mastery of the quantum realm is advancing at a pace that would shock the physicists of a century ago. We are learning the language of the ghost. We stand at a precipice, looking in two directions. One direction looks out at the stars, at the black holes and wormholes. It is the path of space-time geometry, written in the language of general relativity. It is a path of immense power, cosmic engineering, and terrifying physical peril. The other direction looks inward, into the heart of matter, into the quantum vacuum. It is the path of probability and information, written in the language of quantum mechanics and, perhaps, quantum gravity. It is a path of subtlety, of paradox, and of philosophical vertigo. Both paths, according to our best mathematics, lead to the same destination, mastery over time. But they present us with a choice that is more than scientific. It is almost mythological. Do we seek to become like the Titans, seizing control of time by bending the very architecture of the cosmos to our will? Or do we seek to become like the Oracle, understanding time so deeply that we can navigate its paradoxes and illusions, moving through history as silently as a reinterpretation? The universe has shown us both doors. One is vast, heavy, and studded with the jewels of dead stars. The other is infinitely small, hidden in the spin of an electron, and locked with a cipher made of probability. The question for the next chapter is no longer, can it be done? The equations whisper that it can. The real question, the terrifying and beautiful question we must now face, is this: what kind of creatures would we become if we stepped through either door? A young woodcutter, lost in a forest at dusk, stumbles upon a small, perfect cottage made of gingerbread and candy. He's starving. He breaks off a piece of the sugar-pane window and eats it. From inside, a voice calls, "Who's nibbling at my house?" Terrified, the woodcutter runs. He runs all night, and at dawn, exhausted, he finds himself back at the gingerbread cottage. The piece of window is missing. The voice calls again. He had been running in a circle. This is the oldest fear, not of monsters, but of loops. of being trapped in a sequence with no exit, where your end is your beginning and your escape is your capture. For the last 3 chapters, we've been the hopeful woodcutter. We've mapped the forest of physics, finding tantalizing paths, wormholes, quantum tunnels, warp bubbles that seem to lead out of the linear prison of time. But now we must stop. We must listen for the voice from the cottage, because the universe has its own ways of asking, "Who's nibbling at my house?" Its questions are called paradoxes, and they are not just logical puzzles. They are fundamental objections written in the language of causality. They are the universe's immune system reacting to the infection of a contradiction. Before we can even think about building a machine, we must face the paradox police, and their interrogation is merciless. Let's start with the most famous officer on the force, the one with the battered notebook and the cynical glare. Meet the grandfather paradox. The formulation is simple, brutal, and personal. You build a time machine. You travel to a time before your grandfather conceived your parent. You kill your grandfather. Therefore, your parent is never born. Therefore, you are never born. Therefore, you could not have built the time machine, traveled back, or killed your grandfather. Therefore, your grandfather lives. Your parent is born. You are born. And you build a time machine, travel back, and kill your grandfather. The loop is closed. The logic spins, frictionless and impossible. It's a perfect Ouroboros of contradiction, eating its own tail. It's the gingerbread cottage with a corpse on the doorstep. For decades, this was considered the knockout argument against backward time travel. See, physicists would say, it leads to a logical impossibility. Therefore, it cannot happen. The laws of physics must forbid it. Stephen Hawking famously invoked this with his chronology protection conjecture, idea that the universe has a built-in mechanism, perhaps quantum effects around time loops, that prevents paradoxes from occurring, thus making the past safe for historians. But is that the end of the story? Does a logical paradox in our minds necessarily translate to a physical impossibility in the universe? To answer that, we must move from the interrogation room to the laboratory. We must run the experiment. Imagine we have our primitive time machine. It's a two-way wormhole time machine, like the one we described. Mouth A is here, in the lab. In 2045, Mouth B has been on a relativistic journey and is now permanently stationed in 2025. You can step into A and exit B in 2025. Now, we design an experiment, not with a grandfather, but with a logic bomb. In the lab 2045, we build a simple device, a steel box. Inside is a single photon, a detector, and a gun. The mechanism is as follows. If the detector registers a photon, the gun is armed. If the detector registers no photon, the gun is disarmed. The gun is pointed at the box's own time machine, mouth A. If armed, it will fire a bullet into the mouth the moment the experiment begins. The experiment has one other element. We aim a laser at the other mouth of the time machine, mouth B. Sitting in 2025, the laser is set to fire a single photon into mouth B at a specific time in 2025. Here is the causal loop we create. The laser fires a photon into mouth B in 2025. The photon travels through the wormhole and emerges from mouth A in 2045. 2045. Experiments start. The photon hits the detector in the steel box in 2045. This arms the gun. The gun immediately fires a bullet into mouth A. The bullet travels back through the wormhole and emerges from mouth B in 2025, just in time to intercept and destroy the laser before it can fire the photon. No photon is fired in 2025, but if no photon is fired in 2025, then in 2045, no photon emerges from mouth A to hit the detector. The gun is never armed. The bullet is never fired. The laser in 2025 is never destroyed. Therefore, the photon is fired in 2025, and around we go. What happens? Does the experiment explode? Does the universe freeze? Does a black hole spontaneously form in the lab? This isn't just a thought experiment. Variations of it have been rigorously analyzed by theorists like Igor Nevikov, Joseph Polchinski, and others. They've treated it not as a narrative, but as a physics problem. You plug the initial conditions into the equations of motion for the photon, the bullet, the laser, and you ask, what consistent solution exists? And a remarkable thing happens. The equations do yield consistent solutions. Not one, but many. One consistent solution is trivial. The bullet emerges from mouth B in 2025, with just the right trajectory to nudge the laser, not destroy it. The laser fires, but the photon is slightly deflected. It travels through the wormhole, emerges in 2045, and hits the detector at an angle that only partially arms the gun. The gun fires a bullet that is slightly off target, which emerges in 2025 to give the laser the exact same nudge, and so on. A stable, self-consistent, non-paradoxical loop. The universe's answer to the logic bomb isn't NO. It's let's negotiate. It finds a stable, non-contradictory equilibrium within the loop. The past is not changed. It is fulfilled. This is the essence of the Navikov self-consistency principle. The only sequences of events that can occur are those that are globally self-consistent. You cannot create a paradox because the initial conditions of the universe, including the existence of time machines, only allow for history that is paradox-free. In this view, the paradox police are not preventers. They are enforcers of consistency. They don't stop you from going back in time. They ensure that whatever you do back there, it's what you always did. This is a profound and eerie idea. It suggests a universe that is not a linear narrative, but a fixed four-dimensional sculpture. Every time loop, every journey to the past, is just a curlicue in the sculpture, carved in stone from the beginning. Free will, in the context of changing the past, becomes an illusion. You have no more freedom to kill your grandfather than you have the freedom to suddenly turn into a potted plant. The geometry of space-time forbids it. But is this satisfying? Or is it just a fancy way of saying time travel to the past is boring, that you're just a puppet acting out a pre-scripted role in a history that already includes you? There is another precinct in the Paradox Police Department. It deals not with prevention, but with proliferation. Its chief officer is the many worlds interpretation of quantum mechanics. The many worlds officer takes one look at the grandfather paradox and shrugs. The problem, he says, is that you're assuming there's only one timeline. There isn't. Recall Schrödinger's cat from chapter 3. In many worlds, when you open the box, the universe splits. One universe has a live cat, one has a dead cat. Both are equally real. Apply this to time travel. You step into your machine intent on killing grandfather. As you travel, or as you pull the trigger, the quantum uncertainty of your actions causes the universe to branch. In one new branch timeline beta, you succeed. Grandfather dies. You are never born in that branch. That timeline continues with a mystery, a dead young man and a vanished assassin. But the original branch timeline alpha, the one you came from, where you were born and built, the time machine remains completely untouched. It's still there. You didn't vanish from it, because the you who left is now in timeline beta, in timeline alpha. You simply disappeared into a time machine and never returned. Your grandfather lived a full life. Your parent was born. You were born. History is unchanged. The paradox is solved not by consistency, but by branching reality. The police don't stop you. They just file your crime in a different, parallel universe. This feels more satisfying to our sense of agency. It preserves the possibility of change. But it comes with a devastating emotional and philosophical cost. If you travel to the past to prevent a tragedy, a war, an accident, the death of a loved one, and you succeed, you haven't saved your loved one. You've created a new, adjacent universe where they live. The you in that new universe gets to be happy. But the original you're either stranded in this new timeline, a refugee from a tragedy that never happened here, or you're gone. The original timeline, with all its pain, still exists. You haven't erased the suffering. You've just abandoned that world to it. Is that time travel, or is it cosmic desertion? The Paradox Police have a third, even more mind-bending officer on duty. This one doesn't carry a gun or a rule book. He carries a mirror. Meet the bootstrap paradox, also known as the ontological paradox. Ontological means concerning the nature of existence. This paradox asks, where did the information come from? Imagine you are a budding composer in 2025, but you're struggling. You have a time machine. You travel to 1800 and visit a young, unknown Ludwig van Beethoven. You hand him a complete, perfected sheet of music for his 9th symphony. Here, you say, this is your masterpiece. You will finish it in 1824. Beethoven studies it, is amazed, and copies it out in his own hand. Over the next 2 decades, he presents it as his own work. It premieres in 1824 to universal acclaim. The symphony is published, copied, recorded, and passes down through history. In 2025, you find a copy in a library. You then take this copy back to 1800 and give it to Beethoven. Question: who composed Beethoven's 9th symphony? Not Beethoven. He just transcribed what you gave him, not you. You just copied what history said Beethoven wrote. The symphony has no origin. It is a closed loop of information with no creator. It exists, but it was never created. It is an ontological phantom. This isn't just about music. It could be about the blueprints for the time machine itself. What if you receive the schematics from your future self? You build the machine, then later go back and give the schematics to your younger self. Who invented it? The bootstrap paradox removes causation from the equation. Effect precedes cause, or rather, cause and effect are codependent in a loop with no starting point. The Nevikov principle would say this is finite, a consistent loop. but it challenges our deepest notions of creation, invention, and origin. It suggests reality can contain causeless facts. Some physicists, like David Deutsch, have suggested that such bootstrapped information wouldn't be stable. Tiny quantum fluctuations would introduce noise into the loop each cycle, eventually corrupting the information. The symphony would degrade over iterative loops until it became nonsense. The loop needs an external source of stability, an unmoved mover outside of time. But in a purely closed, time-like curve, there is no outside. Then there is the most psychologically unsettling officer of all, the predestination paradox. This is the universe as a sinister playwright in this scenario. Your attempt to prevent an event is what causes it. Classic example. You learn that a fire killed your parents when you were a child. Grief-stricken, you build a time machine, go back to the night of the fire, and manage to rescue them. As you lead them to safety, you knock over an oil lamp you didn't see. It ignites the curtains. The house goes up in flames. You have caused the very fire you came to prevent. Your childhood memory is of being rescued from a fire by a mysterious stranger. Who was you? But the universe, it seems, loves nonsense. For over a century, experiments have confirmed, again and again, that superposition is real. Not for cats, we think, but for electrons, photons, and even molecules large enough to be seen under a microscope. They truly exist in multiple states at once. What does this have to do with time? Everything. Superposition violates our classical notion of a single, definite timeline. In that box, for an hour, there isn't a single history where the atom either decayed or didn't. There are two histories, both equally real in the quantum description. A branching path of reality. This is the seed of the many worlds interpretation. Proposed by Hugh Everett in 1957, Everett took superposition deadly seriously. He said, "The wave function never collapses. Every possible outcome of a quantum event actually happens. But it happens in a newly branched, parallel universe. When you open Schrödinger's box, you split in two. In one universe, you see a live cat and feel relief. In another, you see a dead cat and feel horror. Both views are real. The timeline doesn't resolve. It proliferates. This interpretation provides a stunningly elegant, mind-boggling solution to our oldest time travel paradox. The grandfather paradox. If you travel to the past and prevent your grandfather from meeting your grandmother, you don't vanish in a puff of logic. According to many worlds, you simply branch off into a new parallel universe where you were never born. Your original universe, where you were born and later built a time machine, remains untouched. You haven't erased yourself. You've just emigrated to a timeline where you don't exist. Time travel, in this view, isn't journeying along a single, fragile thread of history. It's hopping between branches of an infinite, ever-branching quantum multiverse. The paradox isn't resolved. It's sidestepped entirely by an infinity of alternate realities. But is this a mechanism for time travel, or just a convenient escape clause for its paradoxes? To find a potential quantum engine, we must go deeper. We must look at how particles themselves seem to treat time as an optional concept. In the 1940s, the brilliant and iconoclastic physicist Richard Feynman developed a visual shorthand to calculate how particles interact. In these diagrams, time usually flows left to right. An electron moves along, emits a photon, gets deflected. But Feynman made a radical suggestion. He proposed that the mathematics of quantum electrodynamics worked perfectly if you viewed a positron, the antimatter counterpart of the electron, as an electron moving backwards in time. Think about that. Not as a metaphor, as a literal description. A positron has the same mass as an electron, but a positive charge. In a Feynman diagram, you can draw an electron and a positron annihilating into a photon. Or you can draw a single, continuous world line, an electron moving forward in time, then reversing its direction in time, becoming a positron, then reversing again, becoming an electron. The math is identical. The predictions are identical. The universe, in its most fundamental accounting, seems indifferent to whether it's dealing with antimatter or matter traveling backwards in time. This is more than a cute mathematical trick. It suggests that at the quantum level, the arrow of time is not fundamental. The equations work. A particle's world line can zigzag through time as easily as it zigs and zags through space. Of course, we never see tennis balls flying backwards into our hands. The macroscopic arrow of time, driven by entropy, is overwhelming. But in the quantum basement of reality, the doors between past and future may not be locked. They might just be very, very small. This quantum ambivalence about time's direction leads us to one of the strangest, most debated phenomena in all of science: quantum retrocausality. The idea that effects can, in some sense, precede their causes. The classic setup to probe this is the delayed choice experiment, an extension of the famous double-slit experiment dreamed up by John Archibald Wheeler. In the standard double-slit, you fire particles like photons, one at a time, at a barrier with two slits. On a screen behind the barrier, an interference pattern emerges, a series of light and dark bands. This is a wave phenomenon. It means each individual photon is behaving like a wave, passing through both slits at once and interfering with itself. The photon is in a superposition of going through the left slit and the right slit. Now, if you place a detector at the slits to find out which slit the photon went through, the interference pattern vanishes. You get two clumps behind the slits. The act of measurement collapses the superposition. The photon is forced to choose one slit, and it behaves like a particle. Wheeler's delayed choice twist is diabolical. You wait until after the photon has already passed through the slits when, by all classical reasoning, it has already decided whether to act as a wave or a particle, and then you randomly choose whether to insert the detectors or not. The result, the pattern on the screen, always corresponds to your later choice. If you insert the detectors after the photon has passed the slits, you get particle clumps. If you don't, you get wave interference. It's as if the photon's behavior back in time is determined by a measurement you haven't made yet. The future is influencing the past. Interpretations vary wildly. Some say this just shows the fallacy of thinking the photon had a definite path before measurement. Others see it as genuine retrocausal influence. But the experimental fact is stark. In quantum mechanics, the distinction between before and after a measurement is not as clear-cut as our intuition demands. This gets even weirder with quantum entanglement. What Einstein called spooky action at a distance. Take two particles, and entangle them, link their quantum fates. Send one to a lab in London, the other to a lab in Tokyo. Measure a property of the London particle, say its spin. Instantaneously, the Tokyo particle's spin will be correlated. It will be the opposite or the same, depending on the type of entanglement. This correlation happens faster than light. Information seems to leap across space. Now, add relativity's shifting perspectives on time. From one observer's frame of reference, the measurement in London happens first, causing the state in Tokyo. From another observer's moving frame, the measurement in Tokyo happens first, causing the state in London. Which is the cause? Which is the effect? The universe refuses to say. The math works perfectly both ways. Entanglement creates a correlation that is timeless. It links particles across space in a way that seems to exist outside of a clear temporal sequence. Could we exploit this? Could we use entanglement to send a signal not just across space, but across time? The idea of a quantum time crystal provides a tantalizing, though speculative, hint. Proposed by Nobel laureate Frank Wilczek in 2012, a time crystal is a hypothetical quantum system in its ground state lowest energy that nevertheless exhibits periodic motion. It's like a clock that ticks forever without any energy input, breaking time translation symmetry. While the first experimental time crystals are fragile, periodic structures in time, not engines, the concept points to a profound idea. Quantum systems can have complex, stable behaviors in the time dimension itself. They are structures of time, not just in time. Now, combine these pieces: entanglements, timeless links, retrocausalities, blurry arrows, and the possibility of quantum structures in time. Could we engineer a quantum circuit, a sequence of entangled particles and carefully timed measurements that creates a closed loop of causation? A microscopic, closed time-like curve for information. Some theorists, like David Deutsch at Oxford, have explored this with the concept of quantum computers, closed time-like curves, QCCTCS. The idea is to use the weird logic of quantum mechanics to perform computations where an answer from the future of the computation is sent back to help compute itself. The math suggests such circuits could solve certain problems, like factoring large numbers with outrageous efficiency. They would literally use time travel as a computational resource. But if information can travel in a loop, even in an abstract quantum circuit, does that not prove the principle? Does it not show that the universe, at its quantum core, permits temporal loops? Yet, for all this quantum weirdness, we keep bumping into the same frustrating scale problem. We can make a photon seem to retroactively decide its past. We can entangle a handful of atoms. But how do we scale this up to move a human, or even a molecule, through time? This is, of course, the most speculative idea of all. But it brings a strange comfort. It suggests that the paradox police are not external enforcers. They are us. The laws that seem to forbid meddling with time are the very laws we, as time travelers, put in place to ensure our own existence. We are both the criminal and the cop, the woodcutter and the voice from the cottage. So, where does this leave us? We have met the paradox police in all their forms. We have seen that they do not necessarily present a veto, but a set of severe, non-negotiable conditions if we wish to build a time machine. We must design it to be consistent, or branch creating, stable against vacuum collapse, precise enough to avoid unintended consequences, perhaps even self-aware, capable of computing its own place in a predestined loop. The challenge is no longer just about energy and exotic matter. It is about logic, engineering. It is about building a system that can navigate the four-dimensional maze of cause and effect without hitting a dead end of contradiction. This may be the ultimate filter for an advanced civilization. Not the ability to harness a star's energy, but the wisdom, more the cold, mathematical capability to manipulate time without unraveling themselves or reality. Perhaps this is why we see no time tourists. Not because it's impossible, but because any civilization stable and clever enough to build a time machine is also wise enough to understand the paralyzing responsibility it entails. They look at the paradoxes not as obstacles to overcome, but as warning signs too glaring to ignore. They become not time travelers, but time curators, guardians of the immutable past, or they become time gardeners, carefully pruning the branches of the multiverse, knowing that with every new branch, they create a whole new world of joy and suffering. We set out to ask if time travel is possible. We have found that the laws of physics, in their deepest language, seem to say yes, but the but is everything. It contains all of causality, all of logic, all of our fears about fate and freedom. The paradox police have not arrested our dream. They have issued it a permit with 1,000,000 restrictive covenants. And so, we are left with the most personal question of all, one that no equation can answer, given what we now know about the price, the loss of freedom, the weight of responsibility, the risk of annihilation, or the ache of cosmic loneliness. Would you still step into the machine? This is the blueprint. It is speculative, outrageous, and built on 1,000 ifs. But it is grounded. Every component, no matter how far-fetched, is an extrapolation from a real theory, a real equation, a real glimmer in a physicist's eye. We are going to synthesize everything: the gravity of Chapter 2, the quantum weirdness of Chapter 3, the paradox policing of Chapter 4, into a single, monstrous, beautiful engine. Let us call it the Chronos Project. And let us begin not with the machine, but with the civilization that could dream of building it. The civilicito, to build a Chronos device. You do not start with metal and wire. You start with a society that has transcended scarcity, conflict, and perhaps even planetary identity. A Kardashev Type 3 civilization, one that harnesses the energy output of an entire galaxy. They are not gods, but they are masters of physics on a scale we can barely comprehend. Their tools are not wrenches and welders. They are quantum gravity manipulators, devices that can gently tease apart the fabric of space-time, not with brute force, but with the precision of a surgeon, separating conjoined twins at the subatomic level. Planck-scale forges, factories that operate at energies of 10-19 GeV, where the distinction between matter, energy, and information blurs, allowing them to craft materials with impossible properties, causal logic engines, computers that don't just calculate probabilities, but navigate the branching garden of the multiverse, solving the four-dimensional consistency equations in real time. This is who builds our machine. Not us, not yet. But to understand the machine, we must think like them. The foundation stabilizing the VOIDL. Time travel concepts that involve traversing space-time. WARP. Bubbles require exotic matter with negative energy density to hold them open against gravitational collapse. Our first and greatest task is to manufacture this substance in macroscopic, stable quantities. Our blueprint turns to the dynamic Casimir effect. As we discussed, the static Casimir effect produces a tiny negative energy density between two plates. But if you vibrate one of those plates at near light speeds, or modulate its properties with extreme frequency, you can amplify the effect, literally shaking virtual particles out of the quantum vacuum and converting them into real photons, while leaving behind a region of sustained negative energy. Our Chronos project envisions not plates, but quantum vacuum oscillators, rings of coherent matter constructed from degenerate neutronium, spun and vibrated at precisely calculated resonant frequencies. They would be placed in a perfect vacuum within a causality-shielded chamber, a region of spacetime artificially flattened to prevent external quantum noise from interfering. These oscillators would pump the vacuum, not for radiation, but for the residual negative energy shadow left behind. This energy would be harvested and stored in topological capacitors, but stable knots in space-time geometry that hold the negative energy density in a metastable state, like a bubble of less than nothing suspended in a field of something. The engineering is apocalyptic. Maintaining the vibrations requires energies on par with a supernova, contained in a volume the size of a city. The shielding requires manipulating gravity at the Planck scale. But for a Type 3 civilization, it is a matter of scale, not magic. This is their heavy industry, the structure weaving the WORHOLE with a reservoir of exotic matter. We can create and stabilize a traversable wormhole, but we cannot rely on naturally occurring ones. We must grow our own. The process begins with a quantum foam catalyst. At the Planck scale, spacetime is believed to be a frothing sea of virtual wormholes, constantly blinking in and out of existence. Our civilization uses a gravity laser-focused beam of coherent gravitational waves to pin one of these nascent wormholes at the moment of its birth. It's like using a pair of cosmic tweezers to grab a single, specific bubble from a glass of champagne before it pops. Once pinned, the microscopic wormhole is fed. Exotic matter is injected into its throat, inflating it like blowing up a balloon. But a wormhole is not a balloon. It is a dynamical geometry. To keep it stable and traversable, its two mouths must be quantum entangled at a macroscopic level. This is done by threading the forming wormhole with a Bose-Einstein condensate of entangled particles, creating a coherent quantum bridge that acts as a skeleton, guiding the exotic matter to form a smooth, stable Morris-Thorne metric, the specific geometry of a benign wormhole. The two mouths, initially co-located, are now separated. One mouth alpha, remains in the construction Forja vast facility orbiting a quiet star. The other, mouth beta, is moved. But not by ship. The engine, moving through time without EMOVing to create a time machine. Mouth beta must experience a different flow of time than mouth alpha. The classic method is to send it on a relativistic journey. But moving a wormhole mouth with a rocket is inelegant and dangerous. Instead, we use gravitational time dilation on an industrial scale. Mouth Beta is not placed on a ship. It is placed at the bottom of a gravitational well so deep it defies belief. Our civilization identifies a suitable Kerr black hole, a spinning one, not to fall into it, but to use it as a gravitational anchor. They construct the Tipler-Hawking orbital array, a series of immense stabilized rings inspired by Tipler's cylinder, but finite and made of exotic matter placed in a complex precessing orbit within the black hole's ergosphere. This array creates a localized region of extreme frame dragging and time dilation, a gravity whirlpool far stronger than the black hole's own. Mouth Beta is positioned at the heart of this artificial whirlpool. Here, time flows at a fraction of the rate it does at Mouth Alpha. Let's say the ratio is 1:10 for every day that passes at Mouth Alpha. Only 2.4 hours pass at Mouth Beta, but we need more than a time difference. We need a time loop. For that, we must connect the mouths and then bring their external timelines into alignment. After a predetermined period, say, 10 years of alpha time and thus 1 year of beta time, the orbital array is carefully powered down. The extreme time dilation effect ceases. Mouth Beta now exists in the same flow of external time as Mouth Alpha, but it is 9 years in Alpha's past. The wormhole bridge connects 2045 Alpha to 2036 Beta. We have created a two-way time machine with a 9-year reach into the past. You step into Alpha in 2045. You exit Beta in 2036. You step into Beta in 2036. You exit Alpha in 2045. Section 4. The navigation system, not where, but when and which a bridge through time is useless without a steering wheel and a map. The challenges are monstrous. Spatial navigation. The Earth moves. The Sun moves. The galaxy moves. If you step out of Mouth Beta in 2036 without accounting for this, you will appear in the empty space where Earth was 9 years ago. You need to target not just a time, but a moving point in space. The loop is consistent. It's paradox-free, but it makes a mockery of intention and free will. Your most heroic act of defiance against fate was scripted as the instrument of that fate. You are not the author of your story. You are a character following a twist you wrote for yourself without knowing it. This is the universe's ultimate gotcha. The police don't block you. They guide your hand to ensure you fulfill your role in the loop. We now have a taxonomy of temporal law enforcement, the Navikov consistency enforcers. The past is immutable. You can visit, but you cannot change. You are part of the scenery, the many worlds branching division. You can change whatever you want, but you're only creating new timelines. Your original home, with its original problems, remains. The bootstrap division. You can create loops of information or objects with no origin. Reality can contain causeless things. The predestination division. Your attempts to change the past are the mechanism that creates it. You are fate's puppet. Each offers a way to resolve paradoxes, but each comes with a profound philosophical or existential price tag. Which one does our universe use? Or does it use a combination? Or does it, as Hawking feared, have a more brutal, physical method of enforcement? This brings us from logic to raw physics. The chronology protection conjecture isn't just about logic. It's a proposed physical law. Hawking and others have suggested that the universe might have automatic, mechanical systems that destroy time loops before they can form. One proposed mechanism involves the quantum vacuum. Empty space is not empty. It's a seething foam of virtual particle and particle pairs, popping into existence and annihilating in accordance with the uncertainty principle. Normally, this is undetectable. But place this quantum foam in the vicinity of a forming closed time-like curve like the throat of a wormhole time machine or the ergosphere of a black hole, and something wild happens as a particle and its antiparticle virtual pair appear. The extreme geometry of the CTC can separate them. One might fall into the past-going path of the loop, the other into the future-going path. They miss their chance to annihilate. They become real particles, and they do this not once, but an infinite number of times, as the same particle can loop through time and meet its younger self. The result? An exponential, runaway buildup of energy vacuum polarization concentrated right at the threshold of the time loop. The energy density would skyrocket to infinity in a flash, overwhelming any conceivable structure and destroying the time machine, and likely a large chunk of spacetime around it in a catastrophic feedback loop. The universe, in this view, protects its history with a minefield of quantum explosives. Try to close a time loop, and you trigger a vacuum energy bomb. The paradox police here are not polite officers. They're a SWAT team with a zero-tolerance policy. But is this conjecture proven? Not at all. It's a compelling argument. But other physicists have shown that under certain conditions, with particular types of quantum fields, or in higher dimensions, the vacuum might not diverge. The jury of theoretical physics is still out. The universe might be safer or more fragile than we think. Let's conduct another thought experiment, one that brings all these forces into play. Let's call it the ultimate test of the paradox police. We build a two-way time machine. We establish a stable communication link between mouth A present and mouth B past 1 hour ago. We then initiate a three-phase test. Phase 1, the Novikov test at t equals 0 in the present. We send a simple, timed signal through mouth A to mouth B in the past. The instruction to the past is, upon receipt, flash a green light in the past lab, visible to our past selves. We, in the present, then look at our historical records from 1 hour ago. Do we see a record of a green light flashing? If YES, Novikov consistency, is demonstrated, the past included the signal from the future. It was always part of history. The police are enforcers. If no, then either the signal wasn't sent, but we just sent it, or the past can be changed. This would be monumental and terrifying.